All right, welcome everybody. So thank you for coming to this talk on opening the floodgates, enabling fast, unmediated end-user access to trillion-row data sets. That should be on ClickHouse, which is we'll talk about throughout the course of this talk. So before I go in, I'd like to give a huge shout out to the Databricks community for sponsoring this conference. Really appreciate how much work you've put in to make it this easy to present. So just a little bit of information about me. You can read the details, but I'm basically a data geek. My day job is CEO for Altinity. We're an enterprise provider for ClickHouse, a very popular open source SQL data warehouse. And we have a couple hundred customers that run everywhere from our own cloud product to a wide variety of on-prem and self-managed environments, everything from embedded systems all the way to huge Kubernetes clusters running in the cloud. And this talk, by the way, will then be based on the experience of working with those customers over the last few years. So what I'd like to do here is just start by framing this trillion-row problem, which is, like what do we mean by that, and what do we mean by some of the adjectives and terms in the title? But I think that before diving into that, it's just simpler to do a demo, which just shows what it's like to work with a trillion-row data set with close to real-time performance. So let's just dash out of this for a second and go run a few queries. So hopefully this will all run. It ran great in the practice runs, and there's not enough of you to disturb the electrons, so it should go just fine. So first thing I'm going to do is count the rows in the data set. So here's my table. This is SQL, as you might expect. I'm just going to hit run and bang. You can read that little number down on the lower right-hand side. That's just over 1 trillion rows of data. So this is a sample data set for sensor readings. It's mostly devoted to, it's got 1 million sensors spread out over a bunch of locations, and they're all collecting temperatures. Let's ask some questions about those sensors. So we'll wipe this query out. And by the way, we don't claim any credit for being able to count fast. That's all just doing that off metadata that's in memory. Let's grab a real query. So pull it up. Put it in, and let's kick it off. So what we're asking here is, what's the maximum temperature that this particular sensor 2555 ever recorded? And what we can see in about 1/3 of a second is that the maximum temperature was 138.23. So that's a pretty quick result. You can see we scanned about 2 million rows to get that out of our trillion rows. So there's some indexing going on, some other aids to some sorting of data that make it run that fast. Let's say we're digging into this and we'd like to find what day that actually happened. Well, we can make a query for that just by extending this a little bit. So let's do that. Again, working on 1 trillion rows here for those of you who are just walking in. Here we go. So let's run that one. And now by adding a little bit of extra information, and in particularly this argmax date temperature, what that's saying is give me the date that was correlated with that max value that you found. Very useful aggregation function. And what we find is that it happened on the 17th of April. Now, in these large data sets and with ClickHouse, I would regard this as somewhat unsatisfactory because we use close to 2/3 of a second. So the question is, if this is something that we're doing constantly, maybe we should put some work in and make it a little faster. Maybe we should pre-aggregate because this is a question that people are constantly asking. So let's do the same query, but instead of doing it on the raw data, we're going to do it on a materialized view, which was actually generated as the data was inserted. We're going to go ahead and run that query so you can see that it's a little bit different, but basically the same. We're going to run that, and that completes in 17 milliseconds. Actually, it bounces around. This is somewhat dependent on caches, so we're down to 7 milliseconds. With the right, I took some kind of conservative design decisions. This could be reduced to 1 to 2 milliseconds. So what these demos illustrate is that you can have trillion-row data sets, and you can get results back off them very, very quickly. Let's go back to the presentation, and now that you've seen this, and begin digging into how we did this. So first of all, just some extensions on the definitions. What do we mean by fast? So in the types of applications that we're dealing with, which are generating metadata for trading systems in financial services, getting real-time information about service logs to diagnose faults in cloud systems, managing content delivery networks, what we mean is consistent sub-second response. Not only that, but it scales linearly with the applied resources. So that, what that really means is as our data set gets larger, we can add more hardware, we can add more storage, and we'll continue to have that sub-second response. Unmediated. What we mean by that is there's no cubes, there's no downsampling, there's no messing around with the data. We're as much as possible going to allow the users to go straight into the source data. For many of these problems, it's great to see aggregates that give you understanding, but if your end users are exploring, they also need to see the original data. And then finally, trillion-row data sets. There are many of these. Obviously, anybody at this conference is familiar with large amounts of data, but some of the things that are listed below, these are huge data sets. A trillion is actually small for many of them. They're often arriving very fast off event streams. Half of our customers, at least, use Kafka or something like it to feed the data in. So this is what we're trying to do. And just why do we need fast access? Without going into a lot of details, as humans explore problems, they need to be able to iterate very, very quickly as they're exploring this data. So these are end users. They're trying to develop trading strategies. They're trying to diagnose problems. They may have a question, and then what they'll do is they'll go in and they'll ask a variety of questions, often unpredictable in advance. That's why we have to have raw data. We can't predict what aggregations they want. They'll quickly explore it, and then they'll come up with an answer. In the case of temperature, these temperature sensors, it might be, hey, we're seeing failures because of a bad firmware upgrade. But it could just as easily be, figuring out a better trading strategy. So this kind of access is very, very important to enable this sort of end user analysis, particularly if you have a lot of them. So the solution is probably a little disappointing. It's put it all in one huge table and make that table really, really fast. So we've heard a bunch of talks here. People mentioned they have 15,000 data sources. They have 200K tables. This is a different class of problem. And in the use cases that we deal with, this turns out to be a really great way to do it. So we put them into the table, and we're going to have unaggregated table data as much as possible. We're not trying to crunch it in advance unless we really have to. We're going to arrange the data in a way that's going to minimize the I/O. So we're going to get it back off storage as quickly as possible. We're going to maximize the applied CPU. We're going to parallelize everything across cores, across CPUs, across machines on the network. And we're also going to keep our intermediate results in RAM. We're not going to be spilling things to disk, and we're not going to be moving data around. So you can still do joins. ClickHouse talks SQL, just like, in fact, most of the, and other data warehouses like Druid, they can do joins, but if you want to solve this problem the way that we're describing, it is, you don't want to do joins between large tables. So, and before you think like, hey, this really isn't worth the money to hear this, what's kind of interesting about this is just making this large table work, and sort of these very, very large tables of rapidly arriving data and linear scale, fast response on it, it's actually a hard problem. And if you go to Knuth, for example, sequential search seems like a totally simple problem. Why would anybody need to look up Knuth for that? Well, it turns out there's some interesting properties. In the same way, as we build these systems, there's some interesting tricks that you need to use in order to get these systems to meet their requirements. Let's dig into that. So I'm going to just start with the blocking and tackling, sort of the basic things that you do when you first load one of these data sets and begin to play around with it and try and get a system rolled out the door. So first, let's just briefly visit the scene of the crime. So we're using ClickHouse here. ClickHouse is kind of like MySQL. It's a single statically linked binary. It's written in C++. It is really, really fast. So we'll talk about some of the tricks, aside from just having well-optimized code. Some of the moving parts that are of interest in this process, of course, you can run many of them on a network. It does sharding and replication and all that stuff. But as you're looking at the process, your query has an execution pipeline that includes your query arrives, it gets parsed, it gets turned over to an interpreter that builds a plan. There is no query optimizer or cost-based optimizer in ClickHouse. It's just all rule-based. And then it has a query pipeline that actually does the dirty work of running it. We'll look at that in detail in a second. And then there's a bunch of memory that's associated with this, with this process. This is not an in-memory database, but we do things like store indexes in memory. So we've specifically designed them to be very sparse, so that even on large data sets they'll fit, so that we can quickly use that to guide the queries. Of course, as we scan the blocks off storage, those are going to appear in memory as we're processing them, but we get rid of them as quickly as possible. When we're joining tables, by default, we're going to pull the join tables, like the right sides of the join, will get pulled into in-memory hash tables, and we'll do a hash join on them. And then, of course, as we're processing a query and sort of jamming through these enormous tables, we're going to be piling up results in memory, again, in hash tables. As far as storage, it's columnar storage underneath. We use block storage, of course, either attached to the device or over the network, or we can read columnar storage off object storage, in which case we have to have a little bit different caching mechanism to make it perform. So that's the process. What does it do what kind of tricks do we use to get this thing to perform? Well, the simple answer on that is practically everything. So just about every trick you've heard about for query performance is probably used somewhere inside ClickHouse. So it's a long list. You can read them: codecs to reduce the data size before compression, skip indexes to identify blocks that should not be read so that we can avoid I/O. A distributed query, being able to run queries, blast them out across, say, 50 nodes or something like that if we need that kind of horsepower, so on and so forth. This is a short talk, so I can't go into all of them, but I'd like to go ahead and illustrate them, starting with just what's the table organization look like. So, because this will actually gather together a number of these tricks. So the workhorse table in ClickHouse is something called merge tree. It's a little bit like a log-structured merge tree, has some sort of similar ideas, but like a lot of table formats, for example, like if you go to Snowflake, it breaks the table into parts. So those are chunks of data that contain all columns and a bunch of rows. They're self-standing pieces, and you can query them independently. You look inside them, each of the rows is stored in a couple of files. They're basically arrays. They are sorted in the same order that you give you have to specify the order in the table definition, and there's a sparse index that's based on that row, on that row sort order. So this allows you, and by sparse I mean that there would be an entry in the index by default about every 8,000 rows. We do this because this index will then fit into memory even with a trillion row data set, like what we're dealing with right here. So on top of that, and you can use that then to, of course, to locate particular positions in these columns. However, you can just scan them as well, because the columns themselves are compressed. We have a number of tricks for figuring out what to read in the columns, even if we don't have an index. And then finally, we have skip indexes. There's about a half dozen of them, but min-max, just saying, hey, within this block, there's values between 5 and 8. So if you're looking for 9, don't look here. Bloom filters, set indexes, other things. So with that organization in mind, we can start by making a table. And as we load the data for beginning to process this data set, we're going to make a table which is going to be pretty simple. Just throw in some basic data types, just kind of guesses. We're not going to do anything with compression, not going to make any decision about using tricks like codecs. We're also not going to specify a way to partition the data or to order it. Tuple is just an idiomatic way to say, I don't care. So we jam this data in, and then we can look at it, begin playing with it using system tables to establish, to say, hey, what's my compression level? As soon as we have that information, we can then make a better table. And what I'm kind of illustrating here implicitly is that in ClickHouse, unlike Snowflake, unlike BigQuery, you actually have to make choices about how to organize data. ClickHouse doesn't do it for you. Moreover, as I said, we don't have a cost-based optimizer. We don't figure out how to do stuff. You make the choices. But if you make good choices, it's very fast. And this is a table that makes much better choices. So the data types are optimized. Make them as small as possible. We use codecs. So double delta is a codec that feeds in data. And basically what it says is, I've got some integers. Maybe they're monotonically increasing. Don't store the integers. Don't store the differences between the integers. Store the differences between the differences, the slope of the slope. This results in certain data patterns, an incredibly small amount of data that then gets turned over to the STD to get pounded and made as small as possible. We use time-based partitioning. It's common in these large data sets to have them time ordered. That tends to be where, how we manage them. And then you have an order by, which is something sensible based on your data, where the values go in increasing cardinality from left to right. And this is really important. This can affect your compression levels because it changes your run lengths. It also affects how quickly you can locate data. And the differences are profound. Just looking, I'm not even considering performance because we can illustrate that, but if you just look at the amount of data you end up storing, my unoptimized initial table definition is about 4.5 bytes per row. The optimized one is about a byte per row, which is pretty impressive. I mean, these are 7 columns, so the compression is huge. I actually chose for the example I just ran on, I used LZ4 for my compression because that's cheap and it makes my input go faster. So these are choices. So I'm going to need about a terabyte and a half of data for this. One other trick that people often use is sometimes you're not totally sure. If you have like a lot of data, many columns, I only have 7, so it's pretty easy. But say you had 100. Well, you might not actually want to make them all columns. You might just want to do something like just store the JSON object. And I've illustrated that here. And then pull the columns out as you need them. So ClickHouse makes it very easy to add columns by sucking the data out of the existing JSON object, for example. Meanwhile, you can actually query on it. You can even do things like put Bloom filters on it. So you have a lot of options for sort of handling this data and creating a system that can then evolve to meet new performance requirements over time. So speaking of performance, I just want to touch on one final area of sort of the initial optimizations, and that's just to look a little bit more closely at the query model. So you have a query which is showing up, it's being handed, it arrives in the server, gets promptly turned over to the parser, we make a nice a syntax tree out of that, we turn it over to the planner, we figure out how to actually execute that, and then what we do is fire up some number of threads. It's usually matched to the number of vCPUs you have in cloud environments, and then we're just going to jam through the data as quickly as possible on each of those threads. So we're going to read we're going to assign them to read different parts of different parts in storage and different columns or parts of columns within them. It's vectorized as much as possible, so we're basically reading arrays into memory. They're designed to align as well as possible with caching. We use SIMD instructions wherever possible to speed this up. Once the results get accumulated in hash tables in memory, often bi-level, because when we merge, we can also parallelize that part as well. So that's the basic query planning, very simple, so there's no elaborate query optimization here. It's just basically jam through this as quickly as possible, and then merge, sort, and then do any, apply window functions, things like that at the end. The scaling on this can be outstanding. So this is an example. On the left is a query that just is asking a bunch of generalized stats on the first 10,000 sensors. It takes a fair amount of processing time. The graph on the right shows the effect of adding more threads, which you can control to this query. So it's a log linear format. So what you can see is as you scale exponentially from 1 to 16 vCPUs or threads, you get completely linear scaling. It tails off a little at the end, I think because we're starting to bump up against the I/O bandwidth limitations. So this has really great performance. So that's the basics. And I think if you went to other data warehouses, you would find that they'd use similar tricks at similar levels, whether you know about them at all. What I'd like to do now is talk about some things that ClickHouse does in these large systems that are unique, at least as far as I know. So we talked about having a single table. Well, what that implies is that most data sets actually have multiple entities. So what that means is we're going to need to have multiple entities in one table. We don't want to do joins between them. We don't want to split them out because in large systems, that would imply, if we join between them, that would imply moving data. Moving data is bad, it's costly, it's nonlinear. So what we'll do is we'll create columns for each of in this simple example, we'll create columns for each of the unique fields in these different types of messages that we're processing with one column that's a discriminator that can tell the difference between them. Second thing we do is we make everything an aggregation problem. Aggregation is fast. ClickHouse does it very well, but it also has some interesting properties that help with scaling in these data sets. Really big thing about aggregation, you don't need to move data to do it in general, because you can scan and just accumulate things as you go along. As long as you don't run out of memory, you can go very, very fast, and you don't have to move things, for example, between hosts or to create temporary files. Second thing, it parallelizes. This is an example of doing a parallel computation of an average. We do sums and we do weighted average, and then we can combine them we can merge them at the end. So this will parallelize, everything from across, hardware threads on a single core, all the way to across many, many hosts on a network. Finally, the intermediate results are reusable. So if you can store these intermediate results, you can build things like materialized views, and as new data arrives, you just compute the partial average on the arriving data, add it to your materialized view, all the other stuff has already been computed for you. So it's a very, very efficient way of handling data. So in ClickHouse then, we do some kind of special things in aggregation. The first thing is we have very powerful conditional aggregation. So we're going to go ahead and, in this particular query you're looking at, what we're doing is counting statistics where the counts vary by the message type. This can be done in other SQL dialects, but ClickHouse takes it quite a bit further. We have these things called if combinators where you can just add arbitrary conditions. In this case, I'm just doing it to the counts, but I could have added it to the max and the min to really only get them from temperature readings. I could do data cleaning right here for different data entity types. It's all done in one scan. So you get that table, that result. You've gone through the data once. You didn't have to scan it multiple times to find this out. So that's really important. But then we can do some kind of interesting things with this because we can do this because we have these additional aggregation features. The next thing is how to simulate joins, because you do want to do joins. And here's an example. Let's say that we want to find out what do temperature readings look like for a sensor after it restarts. So normally we'd do some sort of join where we'd go get find the last restart time, and then we would join it with the records that come after that. So join key is sensor ID, and then we can get temperatures after restart. The reason we're interested in joining is we want to see the uptime on the sensor and see if there's any relation to the temperature that it's reading. This can be done through aggregation. This, by the way, was kind of enlightening when somebody showed me this, but what you do here is instead of having a join key, you have the group by key. That's what joins your data. So the join data is whatever is in that group by. And what ClickHouse does is it has another specialized aggregation function which will actually pull in values as they arrive in the group. And instead of counting them or summing them or taking the max, it puts them into an array in exactly the order that it arrived. And so in this particular join, we just create a couple of arrays which contain the reading time, so the time we took the reading, and then the temperature that we got, and that's what we're aggregating. And then there's a second feature which allows us to pull this back out, to basically flip these arrays back out and turn it into a normal set of rows. So you can see the the array values have been effectively pivoted, and then the outside values, the columns that are joined against it, are then just added in as scalars. So this is a very, very powerful feature. And in fact, this particular query, if I ran it as an example, completes in about a millisecond. Now, I'm only using one sensor, but it is incredibly fast because, again, I'm not having to move data. I'm not having to, to do multiple scans. Here's the code that does that. It's, you may want to study it at your leisure, but it uses this specialized function group array, and it's group array if, so it's only use this function if we're dealing with a message type that is reading. So interesting, definitely probably, if you haven't used ClickHouse, this probably doesn't look like SQL you've seen recently, but it is very powerful and very effective. Final example, locating key events. So in these large tables, you're going to have the problem that you're often going to want to know, hey, when did my device start the last time? When did I get an error on this device? And in conventional SQL, you can find this out, but it's fairly expensive. This query over on the right shows you how to do it. You typically do some sort of in expression, where you're basically going and looking for, in this case, we're looking for, on this device, for the error message with the highest time. So that's the last error message. If your data set is big or the conditions are complex, this is very expensive, especially if you repeat it a lot. So we don't want to do this. And the answer here is, once again, turn this into an aggregation task. So, and in this case, what you can think about is it's a pretty simple idea. You have a couple of different rows on the top. They are the time, the device ID, and the error message. One's a seg fault, one's out of memory. We're going to aggregate these and merge them, and we're looking for the maximum value. And what we'd like to do is get the max. That's easy enough to understand. And we'd also like to capture the correlated row value, which is out of OOM, or out of memory. Aggregation problem. So what we can now do is go ahead and use this. The fact that we can do these aggregations, we can construct materialized views, which compute this automatically. And the power of the aggregation here is that it runs at the time that data is inserted. This is an extremely efficient query. It adds virtually no overhead on inserting data, but allows you to build what is in essence an index on your data that you can then use for other queries. So these are three ways that we use aggregation to process these large data sets and get this sort of linear performance or linear scaling with very, very low performance and consistent results. So I'm going to switch off that now to one last topic. By the way, there's other tricks with aggregation. We use it to handle deletes and updates and things like that, but that's for another talk. I want to talk about one last thing. The point here was to give this data to end users. And I just want to bring up something really interesting that I have seen across a number of systems now. So traditionally, when you're building systems like that, or any data application for that matter, you're going to, there's like 3 or 4 patterns that you use. Most popular one, build a custom UI. SaaS applications do that. On the left, you see Mux. It's a popular video content delivery network. They have wonderful built-in analytics that are based on ClickHouse. These are the guys that actually handle streaming of the Super Bowl, so they know about content delivery. So that's a popular approach. You could use dashboards. In the ClickHouse environment, Superset and Grafana are 2 very, very popular dashboards. There are, of course, others. And then you have data exploration tools for end users, variations on Tableau, Metabase, other products like that. The trick I want to show you is that there is another way. There are tools like Grafana, which have wonderful UIs, but those UIs might be designed to do things like process error messages using their own store, which is called Loki. So what you can do, and I've actually seen this done, is that you construct a Loki gateway, it accepts logQL, and turns it into a ClickHouse query, goes and fetches the data out from this super fast store, turns results back into something that the logQL client expects. At that point, your users can now use the familiar Grafana interface, but under the covers, you've got Loki. This can also be done with Splunk. This can be done, I haven't seen it done yet with Elasticsearch, but I think it's only a matter of time. It's been done with PromQL. It's been done with many others. This is a really an interesting way, because what you're doing is you're allowing users to continue to use things they're familiar with to access these very large data sets. Okay, that's the end of the talk. Let me just do a quick wrap up. So some of the key learnings from these large installations. Big table. It's not just because we can't do joins. It's not just because we can't do SQL. It's because if you want these properties that I've described, large tables are one very effective way to get it, and there are many use cases where this turns out to be great. So you obviously have to make some sound implementation choices. And in the case of ClickHouse, you have to make them yourself. Over time, ClickHouse will do more for you. The secret power is aggregation. It's kind of like learning how to do SIMD programming, if you've ever done that. It's not like you can't just sort of iterate through things and jump willy-nilly to things. Aggregation forces you to think about these problems in different ways. But if you can turn something into an aggregation problem, you can then have this very, very powerful capability where you just get the answer in one scan. And then finally, build gateways. So, and I think this, for me, is one of the most exciting things that I've seen. I think we'll see many more of those. And reward, linear scaling, cost efficiency, high cost efficiency, and happy users. And we've seen plenty of examples of this. I'd like to thank a few people who contributed to this talk. And I'd also like to thank my entire team at Altinity. I'm kind of a dilettante on this stuff. Many of these lessons are drawn from things that they showed our customers how to do. So with that, thank you very much. I'd be happy to answer questions. You can come geek out with me, talk to us at Altinity. We'd love to hear from you, and also to learn from you about how you're handling these types of problems. So thank you very much.
Thank you, Robert. Yep. Can you?
Yeah, is that possible to use the bucket technique when designing a table?
What was the technique? Can you say that again?
Bucket technique.
Pocketing. What is that? I actually don't know what it is, so I'm learning already.
I came from the Hadoop background, and then we had to join like a multi-billion tables to each other.
Yeah.
And then I think one of my team members, they used the bucket technique. Like
bucketing. Yes, absolutely. Yeah. So like dividing up the key space, for example. Yeah, in fact, when you want to do distributed joins on ClickHouse, in effect, you'll do, that's exactly what you do. So you'll divide up you'll have some way, the application designer will just say, hey, I expect to have these keys over here. I'll make sure all the stuff we have to join against is located there. That's exactly what you do. And that's a really important point. It's not that you can't do joins, it's just that you don't want to do arbitrary joins on large tables the way that, for example, you would in Snowflake, where you just don't even think about how to do it. The cost is, you have less flexibility about what you can query, but the benefit is that your queries have much more predictable performance.
Any more questions?
Would it make sense to use ClickHouse for a data lake, taking into account that ClickHouse likes a good structure of the data, but maybe there are some techniques which can be used to transform the data later in time?
Yeah, that is a really interesting question. And actually one of the things that's kind of a revelation, ClickHouse can read Parquet, but it can't use it as a table format. And I think that, so we are able to ingest data from data lakes, so we can read Parquet, pull it in, process it. One of the things you can think about is ClickHouse has a lot more ways of displaying data in some ways than for example, Databricks does. So yeah, I think there's some very interesting possibilities here. One of the things that I am thinking about is, like, could we just use Parquet as the table format somewhat in the way that Photon does? Then that's really interesting, because now you have a real-time query engine with a bunch of different ways of displaying data. So yes, there's some interesting possibilities. You can already do it now because we can ingest and egress data to S3 using Orc, Parquet, whatever format you want.
Thank you.
Well, we can wrap up the session. Thank you, Robert.
Thank you.
Thanks a lot for your time. Thank you.